I'm happy to introduce Sylvain Corlay. He will be talking to us about Xeus Cling.
Hi, thanks Basil for the introduction and for having me here. I think I have met some of you, but not everyone, last year when I attended the Sarajevo meeting. I mean, the year before the end of the world. So today I'm going to talk about Xeus Clean, and which includes a project called Xeus. And so the title is Deep Dive into the Xeus-based Cling kernel for Jupyter. And so what does Xeus stand for? Long story short, it's another way to misspell Jupyter. Just like, Jupyter has a Y instead of an I. Here we use the Greek god instead of the Roman god. So as far as, so for a quick introduction about myself, so I'm the founder and CEO of QuantStack. So I'm going to tell you a bit more about QuantStack in the next slide. And I'm an open source developer, mostly involved in the Jupyter ecosystem. I'm a steering committee member of the project. I'm also a core developer of kernel, which is an initiative to package libraries and software of the open source scientific computing ecosystem in a language agnostic fashion and in a cross-platform fashion. I'm also the co-creator of Voila, Xeus, and the Xtensor C++ tensor algebra library. Beyond development, I do a lot of volunteer work for the community. I'm a director at NumFocus, which is a foundation that serves as a legal entity and fiscal sponsor for projects such as NumPy, Jupyter, Matplotlib, and many more of this ecosystem. And more locally, I organize the Paris meetup. So QuantStack is the company that I founded in 2016. And so what it is, it's an open source development studio specialized in scientific computing. So essentially, we are a team of maintainers of major open source projects of the open source stack, such as Jupyter, kernel, Xtensor, etc. And we provide professional support and development services for this ecosystem. The company is actually registered in France, but the team is scattered in multiple countries in Europe. So we have full-time people in Germany, Spain, France, and in the Netherlands. So yeah, by the way, since I'm supposed to talk for something like 40 minutes, if you have questions during my presentation, please do not hesitate to interrupt, because otherwise it's going to be a long monologue in front of a, like essentially silence. So one thing I wanted to emphasize about Jupyter, and which is not so known, is that Jupyter's architecture was really developed in a language agnostic fashion, meaning that you can use the Jupyter development environment with many programming languages such as Python, R, Julia, Ruby, and many more, and now including C++ thanks to Clean. And this agnosticism is achieved through an extension point to the Jupyter infrastructure called the kernel. And so the kernel is the part of the Jupyter infrastructure that's responsible for executing the code that you type in the Jupyter Notebook, or in the Jupyter console or any other Jupyter frontend. So from the perspective of the rest of the stack, a kernel is simply a process that implements an inter-process communication protocol, and so speaks that protocol. And all you need to do in order to make a new kernel is implement the protocol in question. So if you want to make a new language kernel for Jupyter, you can first, before making one, you can check whether someone has done it before. And so there are quite a few available already, like for JavaScript, C++, Python, Julia, R, Haskell, and many more. And one issue that we have observed is that there is a very, deep, I would say, variance in the quality, a very important variance in the quality of these implementations of the Jupyter kernel protocol. So some of them are really complete and are fully fledged and well maintained, and others are very minimal and may not even work anymore because nobody is really working on them. So if you want to make a new language kernel for a programming language that wouldn't have one, you can either rewrite it from scratch in that target language. For example, if you are making a new kernel for R, you can totally write it in R, and that may be actually a really good choice. However, it's not that easy, because if you want to do your job well, you need to deal with some actually complex concurrent programming models. Like you need to do a lot of multi-threading, or at least some concurrent programming. You need to have some 0MQ bindings available for your language, and deal with some subtle 0MQ internals. You need to cryptographically sign messages and use libraries for this, and properly implement the JSON protocol of the Jupyter messaging protocol. So if you don't want to do all of this, you can use a framework. And at the moment, there are two main frameworks for making kernels for Jupyter. One is IPyKernel, which is actually the reference implementation of the Jupyter protocol in Python and for Python, but which also includes a base class that you can extend to make kernels. And another one is Xeus, which is going to be our main subject here. So to make wrapper kernels, so essentially IPyKernel includes a base class called IPyKernel.kernel-based.kernel, and which implements the language agnostic parts of the protocol, and then you can implement the language specific parts in a derived class. So this is actually the approach used at the moment for like the kernel linked, the kernel that is shipped with Cling in the main Cling repository. Basically, this kernel makes use of IPyKernel and exposes to Python some of the Cling APIs required to make such kernel. And so there are some issues with this approach, especially if you are dealing with a very simple programming language, for example. One is that you have a dependency on the Python runtime. And for some people, that may be an issue. For example, if you are making an R kernel for the R ecosystem, people may not be super happy with installing Python and having to deal with an entire Python environment just for that, just to make something that should essentially be an executable. And actually, depending on the Python runtime, has some consequences in terms of packaging. So for example, in the case of the Clean project, anything that depends on Python is going to have, when you package it for Cuda, as many variants as there are Python versions. And so that multiplies the number of versions of the package that you have to make, which is not such a big deal because it's all automated in CudaForge. However, it's not super efficient. And so what I think we should do in general is try to split libraries and to have a good separation of concerns between, the core of Cling, the plugins, the kernels, etc. And also more generally, and not just for Cling, or like, the wrapped interpreter that you are trying to expose may not have a Python API, and you need to make one. So in the case of the Cling kernel that is shipped with Cling, there is a Python extension module that was made to expose the proper symbols, apparently. And so in the opposite, one thing that may be also required if you want to use advanced features of the Jupyter protocol, such as Jupyter Widgets and whatnot, you also need to expose an API to the target language in order to let that language explicitly send messages for example, updating the state of a widget or something like this. So in many cases, a native implementation in the target language may be more efficient. So Xeus is a modern C++ implementation of the Jupyter protocol. So it's not a kernel, right? It's just a tool to make new kernels. And it provides a base class, just like IPyKernel, a C++ class that you need to inherit from and implement a few virtual methods to make your own kernel. So that X interpreter base class is actually like the main extension point to Xeus. There is another one which governs the middleware implementation of Xeus and how it communicates with the client. And so that could be used to integrate Xeus into an event loop or communicate over another, means than zero in queue, such as HTTP2 or something like this. So which has been done actually for some projects. And so our motivation for starting Xeus was that we were actually asked by a client to make a Jupyter kernel that was very lightweight for a DSR. And using IPyKernel seemed a bit overkill because they didn't want to actually ship an entire Python environment, and they were really interested in us producing a fully statically linked, executable that would embed their interpreter and implement the kernel protocol. And also, we think that the kernel protocol for Jupyter now is stable enough that it's a good thing for us to provide a strongly typed reference implementation in a compiled language. And finally, most interpreters like R or Python are actually written in C and offer a C API. And so it makes it really easy to embed them into a C++ application. So C++ is a high-level programming language that is a good common denominator for languages such as Julia, R, Python, and obviously C++. And so today there is a full ecosystem of kernels that were written with Xeus. The first one is Xeus Python. So it's a Xeus-based Jupyter kernel for the Python programming language. So I will send you the slides, but I provide the link to the GitHub repository and to the binder. And actually, it's the first implementation of the Jupyter kernel protocol to provide an implementation of the Jupyter debugging protocol so that you can use the new Jupyter Lab Visual Debugger. And it's also used in a project called Slicer Jupyter, which is a Qt application because Xeus has a pluggable, I would say, concurrency model that makes it super easy to embed Xeus into some things such as an event loop or desktop applications. And actually, there are lots of people today who are looking into Xeus Python to embed it into other applications and slicers such as Blender or FreeCAD because IPyKernel does not provide that extension point to change the concurrency model. And I think that should be also interesting for Cling actually, because for the same reasons as for Xeus Python. So Xeus Cling, obviously, so it's a Xeus and Cling-based Jupyter kernel for the C++ programming language. And we really started Xeus Cling as a demonstrator for Xeus. It was just us showing off, and it kind of took off, by accident. Very quickly after we published the first versions on Cuda, lots of people thought it was really easy to install and started using it. And actually now there is a first-year university class every year at Université Paris-Sud using Xeus Cling for teaching C++ to over 300 students through a Jupyter Hub deployment. So they provided us with a lot of feedback, and they tend to make us aware of new bugs very quickly. Another one is Xeus SQL, and there's also Xeus SQLite, which is like a special case. Xeus SQL is a SOCI-based kernel for SQL. And Xeus Robot is a Xeus-based kernel for robot framework. And that is an open source language and framework for robotic process automation. There is the last one, and this one is not something that we have implemented, but I thought you would find it interesting. So L-Fortran is a new Fortran compiler based on LLVM. And beyond the compiler, it actually provides an interpreter, and it includes a Xeus-based kernel. So in the screenshot on the right-hand side of the slide, I am actually providing a small screenshot of the Fortran kernel running in a Jupyter console. So it's kind of close to what you are doing with Cling, but for another language. So I'm going to try to give some live demos here, but it's not a wise thing, so things may crash, so please bear with me, okay? But I have slides of the main things that I want to show, just in case, and also so that people who did not attend the call can, have some of the content. Okay, so this is starting well. So I started this in the binder, so I'm going to restart the binder, and because it expired. And while I restart the binder, I'm going to use the slides for now. So so here you recognize the Jupyter Notebook yeah, this works. Okay. So the first thing I wanted to show is that we actually redirect cout and cr and to the front end, like as you would expect, and catch errors as well. Another feature that you are used to as a Cling user is that if you omit the last semicolon in a cell, you see the value of printed in the notebook for that for the variable. Another thing that is redirected in yeah, I need to import the right thing, but printf, yeah, I need to provide the car. Printf is also redirected to the front end, just like stdcout and stdcr. However, stdclog is not redirected, and it's actually a good way to do some logging in the console, or whenever the console output is redirected to some log file to do some logging of what happens in the kernel. So another feature that is specific to Xeus Cling, and I don't think that something like this exists at the moment in the Cling kernel, is that you can use the question mark to access documentation for types, such as std vector here. And in the case of the standard library, we're going to redirect to the proper section of CPP reference. And actually, that thing is extensible, so you can provide the on-the-fly documentation for your user-defined types. So, for example, we have done it for extensor, and that will redirect you to the appropriate page in the extensor documentation. Yes.
What happens if you do std : the vector of int? Would it?
I think it's going to give you go to vector in that case.
Okay, this is cool, because in principle, what you can do is you can kind of connect it to the diagnostics that are printed out from the interpreter.
Yeah, I think so. Yeah, we could do that. So if you want to look at how to extend that mechanism and make it available for your user-defined types, I recommend looking at the documentation. So it's actually rather easy, and we provide some tooling to actually generate the links from the Doxygen documentation. So it's fairly mechanical, I would say. Another aspect of the Jupyter protocol that I find really interesting is that Jupyter supports rich rendering of variables. So for example, here I am defining a very simple image type, and all that it does is loading a buffer from a file and storing it. And so for that image type, I can overload the MindBundle wrapper function in the same namespace and populate a JSON bundle. And upon display of any instance of that type, I am going to get the MindBundle wrapper rendered in the front end. So this is done through argument-dependent lookup. Potentially anything for which there is a MindBundle either natively in the browser or implemented in Jupyter Lab can be rendered that way, just by providing a JSON representation of the type in question. So you can make rich rendering of tables, data frames, or anything you want. And actually a really interesting example of that is CMagent. I don't know if any of you know CMagent, but it's a really cool project, which is a symbolic program computing. Oh, actually, I need to restart the binder here. Once again, it expired. So I'm going to demo CMagent right after. So what CMagent is a C++ library for symbolic programming, and it's starting to build the entire environment. So I won't be able to show it right away, but and you can do like simple-like operations in C++. And here, using the rich MIME type rendering features of Jupyter, you can render equations using mathjacks inline as you go. And so this really shows that using Cling and the Jupyter Notebook and the rich MIME type rendering, you can have a user experience very similar to that of the Python kernel with Jupyter. On that page, actually, I'm also showing some rich rendering through tables of extensor data structures, and also Xframe, which is a data frame implementation in C++. And last but not least is the Jupyter Widgets implementation. So I don't know if any of you are aware of Jupyter Interactive Widgets, but they are special objects that can be which when you render them inline in the Jupyter Notebook, provide a component that you can interact with graphically, and whose state is synchronized with the backend. So I wanted to give a demo of that. So I'm going to do this right away. And while the CMagent binder is building. Yeah, I'm not using like environments on my local computer right now because the one I'm using, I work on a Linux machine and I have lots of issues with Zoom on it. So that's why I'm using only binder. This is me trying to make live demos and being bitten by binder rebuilding things. So yeah, so Jupyter widgets are special objects that, when displayed in the Jupyter Notebook, provide like a graphical representation and can be used to build UIs. And actually, they have this. They have this feature that they are mostly implemented in JavaScript, and the reference implementation in Python actually is very thin, meaning that there is very little logic implemented in Python compared to the JavaScript. So by just providing a standard implementation in C++ of the communication protocol of IPy widgets, you can leverage all of the Jupyter Widgets ecosystem with very little code. And so in the demo that I'm running here, I'm actually demonstrating that. So here I'm just, for example, including a slider, displaying it in line. If I set the value from the Python, this is going to be reflected visually. If I move the value and display it in the notebook, I'm going to be able to read it. I can modify any aspect of the slider, any property, and that will be reflected visually on the fly. I can redisplay things. We also offer a method chaining syntax to mimic keyword argument initialization. So here's one, and we have lots of these, and actually there are dozens and dozens of widgets. More importantly, actually, Jupyter widgets are more than a collection of controls that will be provided. Actually, they are a framework upon which you can build, and there are dozens of libraries built upon IPy widgets that provide custom controls, such as maps, visualization, 3D plotting libraries, 2D plotting libraries, or anything you can think of, like bindings to graph visualization packages and whatnot. And so in most of these cases, we're in the same situation where like 95% of the logic is implemented in the front end, and the backend only holds like a small portion of it. So making a C++ version of that backend is actually rather easy. So an example for this is Explicit, which is a maps visualization library, and it is actually just a re-implementation of the in C++ of the IPy leaflet backend. Now that actually I have SimEngine installing, I can show this to you, hopefully. There you go. So here I'm just creating an expression. Displaying it in LaTeX, expanding, and seeing the result rendered with Majax inline. Okay, so let's wait for the Xleaflet build. There you go. So Xleaflet is a C++ backend to IPy leaflet, and you can do quite crazy stuff like displaying maps inline. So here we chose like a funny cartoonish backend, base map. You can start, creating some controls and adding them on top of the widget, like the drawing widget. And here I made a callback in C++, just displaying what kind of shape was drawn in the widget. So there you go. So created a polygon, a point, or line string. So yeah, possibilities are endless. There are tons of these libraries out there that are actually rather easy to wrap. And what I would really like to see is more people looking into this and making C++ wrappers for Plotly, for Vega, which we have started a project for Vega, or any other C++ like JavaScript visualization library that you may think of. So back to the slides. So yeah, that one was an example of Xleaflet being used in a C++ notebook for comparing the weather at 2 different days. So if you want to try Xeus Clean, it's actually really easy to install. So we provide a package in CandaForge, so it can be installed with Mamba or Canda. So you can just do Mamba install Xeus Clean, and you're done. You will see the Xeus Clean kernel display in the Jupyter Notebook interface. And this is my last slide. So what are our plans for the future? One of the main things I want to do very soon is provide a Visual Studio 2019 build on CandaForge to provide like a user-friendly way to install Xeus Clean on Windows. We actually do test Windows in our CI, but we don't provide a build for it in CandaForge because right now CandaForge defaults to VS 2017. Also, another thing that I really like to do is in all of the libraries that have a compiled runtime, actually, we worked on adding some clean pragmas in some of the main headers so that the runtime is loaded automatically when you include the cell header. And I think we should be encouraging the authors of the main scientific computing libraries in C++ to do the same in their headers so that you don't need to do any of anything complex to load these libraries and use them in the context of Cling. So that's like the second item. Another thing that we've been working on a lot lately is Voila. And Voila is a tool to transform Jupyter Notebooks into standalone web applications. And it actually works really well with Xeus Clean. And so we've given some demos of that, I think a couple of years ago at in Sarajevo for the CERN workshop, for the root workshop. One thing we'd like to do is actually to provide a tool to build notebooks into a standalone executable that would speak the Jupyter protocol with respect to updating widgets and whatnot, but would be fully compiled and would not depend on Clean or LLVM at runtime anymore. So really provide a binary that would still require Xeus for communicating with the front end and provide a really fast backend to Voila application that does not require, just-in-time compilation. There are a couple of things that I'd love to do with the upstream team if there is interest. I'd really like to do, we have some crazy ideas on how to improve rich nighttime rendering. And also, if there was any interest in the root team in adopting Xeus internally for their kernel implementations, I think that one of the main blocking points right now for root users are the dot comments. And maybe we should provide some kind of extensible magic system, just like in IPython, that would provide all of the dot comments and would also be extensible for anyone to make a new magic. And finally, as I said earlier, so our team is responsible for the development of the Jupyter Lab Visual Debugger. And so this has been done for the Xeus Python and Xeus Robot kernels. And if there was interest, maybe this could be a subject of an internship or something like this about sort of exploring what could be done to implement the Jupyter debug protocol in Xeus Clean to enable visual debugging of clean code in Jupyter Lab. Yeah, that's it for me.
Thank you very much. Very nice talk. Questions?
I have a question, more or less a general question about Xeus and the whole ecosystem. Is there any plans to support GPUs? I tried already with Xeus Cling, so the support of Cuda, and so I tried Xeus Cling together with Cling in Cuda mode, and it works for mostly. And I read also about a little bit your different repositories, and I saw that sometimes also questions about GPU support, for example, also for the extensor framework and so on.
Oh yeah, I was muted, sorry about that.
Yeah, I was also a little bit confused. I thought I was muted.
Yeah, I saw your work on the GPU mode, on the Cuda mode for Clean, and I think this was a great addition. So as I said earlier, so a lot of the other Clean Xeus-based kernels that we made were actually funded by clients, and Xeus Clean is something we just did because we thought it was cool. And so our sort of slowness in adding these kinds of features is not a lack of willingness. It's just that we are doing this on our free time, and why Xeus Python and Xeus Robot were funded by people really interested in us doing it. In terms of GPU support in the extensor ecosystem, this is not something that has, extensor was really developed for client projects for us. And this is not something that people have been, speaking of funding so far, but we have been thinking a lot about it and doing our homework about how we should be doing it, should we do it? actually, we even talked a lot to Axel. I think he worked with him quite a bit about how we should approach this issue. And so, yeah, we definitely want to do it. It's clearly in scope for us.
Sounds good, because at the moment we also looking for a NumPy for other project, NumPy equivalent to port our Python applications to C++, and we have abstraction library for GPU development. And in general, Extensor looks nice, but it's only restricted to CPU.
Mm-hmm. So one thing we do in Extensor, though, is that we have a deep integration with SIMD instruction sets.
Mm-hmm.
So which doesn't give the same kind of speed up as GPUs, right? But a lot of the thinking and the chunking and of the work that we had to do for this, I think, will be reusable and reused when we start doing the GPU work. So
okay.
yeah,
sounds good. And just the last time, I tried also to use Xwidget together with Cling Cuda.
mm-hmm.
And I'm really waiting for the Clang 9 update, because this should solve some compiler problems, and hopefully then I can use it together with Cuda.
You could not use Xwidgets with Cuda? Is that what you're saying?
Yes, because there was some weird compiler error at the template, and I tried it with Clang, and I found out it was simply the bug was located in Clang 5, and with Clang 9 everything was fine.
Oh wow, okay, I had no idea. I mean,
yeah,
Xwidget seems to work fine even with Clang 5 so far. So yeah.
But it only happens if you enable Cuda. With normal C++, it works also with Clang 5.
Yeah, so Xwidgets uses a lot of template metaprogramming, and we had to fight really hard to make it work in real time, like reasonably fast with Clean, because we instantiate the templates at runtime. And so, yeah, there was a lot of thinking put into reducing the compilation complexity while keeping all of the features.
Okay, thanks. More questions?
One question for me. You were talking about debug support on your last slide.
Mm-hmm.
Maybe this is interesting for everyone. Did you make any research about debugging in Cling at all so far? Because it's runtime compiled and it doesn't quite. It's not quite trivial to debug.
Not really. The only thing is, I know that there are, so the Jupyter Debug protocol is essentially a wrapped version of the DAP, the Debug Adapter Protocol from Microsoft.
Okay.
And plus a few things, because obviously the Debug Adapter Protocol was really meant for, I would say, programs and not notebooks or not things that you execute on the fly. And so we made additions to the protocol. And then later on, actually, we talked to the folks who were doing it, because they started supporting debugging in notebooks in VS Code. And we were reassured that they had to do the same additions by themselves without communicating with us. So meaning that we didn't do something crazy. And so I know that there are some DAP implementations for the C++ programming language that work well with Clang. So I have good hope that, reusing our front-end work, reusing what we've done in Xeus core, it should be possible to do it.
I think so. My question targets to the point that for debugging to the code, you can either go like a way that LDB does to store compiled objects on disk, or use the GDB JIT interface that is implemented in some of the backends in LLVM, but it's not like just working out of the box everywhere. And just as a note, if anyone's interested in that, I implemented this for JIT-link in LLVM recently, and also fixed the bug in LLDB, so it could be test it there. And if you are interested in doing that for Cling, just reach out, and maybe there's things we can do together, or I don't know.
Oh, yeah,
Yes,
that'd be
yes,
fantastic.
yes, totally. So we want to have this even this year. So this is Axel. Hi, Sylvain, super presentation. Thank you very much for doing that. And yeah, so we're trying to get the debug symbol connection to the debugger implemented this year. That's on our plan. So yeah, I'll totally reach out. We are not using the JIT linker though, because as you probably know, that's after our current org-JIT implementation that we use in LVM9. So we have to see how we do this, whether we first need to move to org-v2 or
you can do it with runtimedyld. It is currently from the feature set. It's the same. It's at the same level. It works for ELF on x86-64.
Right.
That's basically it.
Yeah, I remember. I actually implemented this in LVM, I don't know, dark ages, many years ago. And there it was working, but then it broke at some point. So yeah, I remember it was working. It's very nice to have. So yeah, I'll contact you. Thank you.
Okay, cool, yeah.
That would be awesome. And we'd be thrilled to put work into this on our side. And just FYI, actually, for another project, which has nothing to do with Cling, we work like very often with someone who is also an LLVM core dev, and so maybe a good person to help.
And by the way, thanks for the presentation. It's very interesting. I didn't have an idea about like what's possible in there. Like that was very, very fascinating. Thanks.
Okay, looks like there is some collaboration there on the debugging. So I just wanted to say that it's also interesting for us to collaborate on that point. So we may probably have a dedicated meeting about that. More questions or comments? We don't have a lot of time.
Yeah, I heard you, Sylvain, regarding the our root Jupyter kernel. I'll discuss that with the person who knows these things when he's back. Let's just see. Maybe we should just send you an email, explain where we see our difficulties, and then you destroy them and explain to us that everything will work, and then we're ready to go.
I'm sure that there will be work, but so I think Xeus Clean is essentially the work of fanboys. So yeah, we would be super happy to put a lot of love into making this work for you guys. And
Thank
so
you very much. Yeah,
I mean, like as soon as I got into Jupyter, I wanted to make this work for Clean, and I made a very first dirty attempt at a Clean kernel before there was one in Clean, and so like a long time ago, because yeah, I think this is awesome. And so I'm probably the only one in this call to not be, you know, like a physicist or working in high energy physics, but yeah, this is great, and so I'd love to spread more the good word about Cling and, you know, interpreted C++.
Thanks.
Okay. We have time for one or two more questions. If there are none, I had like a bunch of questions, but I cannot fire them all at the moment. So I probably will reach out on various things. But one thing that's pressing was that we had I have a question: whether can we pass flags to the Xeus Clean kernel? Like, I saw that there are flavors of like C++14 and whatever, and I'm kind of I kind of know the answer, but for example, for things like automatic differentiation, we are going to need it. That means that I want to be able to say Xeus Cling minus F something and then run in a Jupyter Notebook. Is that possible?
So at the moment, we do explicit parsing of the command line arguments. But I think what we should probably be doing is do a pass-through to anything that we don't understand to Cling, or maybe something like this, so that you can pass anything.
yeah, this would be a super huge enabling factor also for automatic differentiation, but for Cuda as well.
Yeah.
I remember that for the regular Jupyter, for the the Python Jupyter, whatever is regular kernel, you can just define multiple kernels, kernel kinds, whatever you call that, and pass arguments in there. Maybe that would also be an option even today.
Oh yeah, we can generate multiple kernel specs, and there has been a long-standing discussion within the Jupyter community about enabling parameterizable kernel specs, so that upon starting a kernel, you choose values for parameters in a form like I want C++ 17. Instead of having 3 kernels for 14, 11, and 17, you could decide as a parameter. And these parameters would mostly be saved in the notebook so that you don't need to specify them when you open a notebook that already has a kernel associated with it.
Yeah, but Vasil, even today, that is your solution. That should work.
Yeah, so making multiple kernel specs would definitely work. Yeah.
Like a kernel per option. Yeah, that's kind of combinatorial.
Yeah, that's why that's
Yeah.
something we should work on. It's not that complicated actually. We even have a very well specified plan on how to enable parameterizable kernel specs. It's just a matter of someone funding it and or doing it, getting to it.
Yeah, this is good to know. I wanted to make sure that I communicate our needs as well, and we'll see if you can speed that up or we do something about it. Okay. Thanks a lot, everybody. We don't have time to make a roundtable. We will keep in touch. Our next meeting is May the 6th, and I wanted to thank again Sylvain, who spent some time with us and prepared these wonderful slides and discussion.
Thank you.
Thank you very much. Talk to you soon.
Bye.
Bye-bye.
Thanks again. Bye.
Bye.